Good morning. Just a little correction from previous lecture notes. So in the previous lecture, we were reviewing probability and statistics concept here. So one of the end of the lecture, we were talking about white noise. Basically, we said, okay, there's a white noise process W of n, which has a zero mean and a certain variance. And then we said the autocovariance and the correlation of this white noise process, which is written as this. So basically, you're looking at the covariance between Wn and the W of n plus k. So there's a case instance of a difference between these two at here. So as a matter of fact, what I'm writing at here, it's not this matrix, right? This one here, it's sigma squared delta k. It's this, right? So what does that mean? This basically means, okay, it equal to sigma square with k equal to 0. So delta k is the delta, it's a Dirac delta impulse function, right? And then it's 0 when k is not 0, okay? Yeah. So basically, we're talking about the white noise process. You have W of n, W1, W of n at here, right? Okay. So all of this bunch of data here, okay, and compared to this bunch of data here, they're basically independent. Okay, they're basically independent here. So all of them have the same basically sigma square, but they're independent. So the covariance between W and Wn plus k is going to be 0 if k is not 0. Okay, so that's just for one process. Okay, it's just one process here. So now today, let's look at more general case now. Okay, yeah. And I'll write down this here, and then we'll introduce a concept called white vector. So now let's talk about common filter. Okay, first the linear model. Okay. So the model we're dealing with here is very much the same thing as in previous lecture. The only difference now is we plug in a noise term at here, okay? A noise term. So this term in terms of output, same thing. So we plug in another term in here. So this W of k here, we generally call it process noise, and the V at here, we call that sensor noise. Okay, so this is a vector, huh? First of all, this is a vector here. This is also a vector here. Basically, if you have multi-output, right? So in terms of diagram, so what this one is basically, you have the process at here. Okay, so this process is basically the state variable equation at here. So now you have the W of k, okay, which is a process noise. It goes into the system, and then at the output at here, okay, so this is your C, let's say x of k at here. So then you have your sensor noise, okay, superimposed, okay, on the sensor here. So this is your output y of k at here, right? Yeah, so that's the general model right here. So the W of k, V of k at here, now what there is basically this W of k will equal to W1 of k up to Wn of k, right? Yeah. And each one of them, okay, now in our case we're going to consider them basically this is a white noise. So this is basically so-called, remember in the previous lecture, right? This is so-called a random vector, right? It's a random vector here. Now, if all of them, we're considering them all as white noise, so this is we consider them as a white vector, a white noise vector, okay? Yeah. Same thing for the V though, huh? Same thing for the V. So in terms of dimension, I think you also need to bear in mind of all the dimensions that we're dealing with at here. Okay, so what's the dimension? The X, okay, is n by 1 vector, okay, and G of course is n by n. So U, so we're talking about maybe multi-input or multi-output system. So the U, maybe there are number of inputs. Okay, and then the W is a n by 1 vector. Okay, yeah. So same thing, and for Y, maybe it's a multi-output system. Okay, n by 1. Then the V is also an n by 1 here. So if we're looking at a single input, single output system, then the V will be just a scalar value, right? It'll be a scalar. So okay. So if it's scalar, then it's just same as the previous lecture. It's just a wide process, wide noise process, just one, right? Okay. Yeah. Okay, so the other thing you also need to remember is, okay, so this is a W of 1k, Wn(k). So this W1k or this W1k represent, or Wn, anything here, represent one noise process, right? One wise process. And at the same time, your W1 of 0, W1 of 1, up to any number, or W2 of 0, or W2 of 1, up to any number. All of this thing here, we call that what? They're random variables. Okay, they're basically all random variables. For each run of your experiment or for each control trial, right? And they all gonna have a different values, right? And so they are basically a random variables there. So some of the properties now associated with the noise. So what are, so yeah, before we move on here, so now if these things are random variables here, or random, basically a noise here, then essentially when you plug those noise into this equation at here, so this x of k, or the response at here, so x1 of 0, x2 of 0, and then up to maybe any numbers you want, right? Or maybe x1 of 1, x2 of 1. So basically all different kind of combinations, okay? And all of these things here, they are also all random variables too, right? Yeah. So some of the properties now. Expected value of this W of k, okay? Expected value. Apparently it's going to be 0 because it's a 0 mean Y noise, right? Yeah. Okay, so there's going to be 0 here. Okay, and same thing for the expected value of the V. It's also going to be 0. Okay. And now we look at what's the W for k. What is the correlation or covariance, okay, for the white vector at here, okay? So this one here is going to produce a so-called covariance matrix, okay? It's covariance matrix. RW is a covariance matrix. Okay, it's kind of covariance matrix. So what this is basically going to be a matrix, and there's going to be sigma square up to this like this, right? Yeah, it's diagonal matrix. Okay. All right, yeah. It could be different. Okay, it could be so W1 here, Wn and here. Okay, so you can assume for the state variable x1, there is this much of variance of noise. For state variable x2, x3, or up to xn, right? Different variance there. Okay. And expected value of V is going to be another covariance matrix. Okay. So this is also another covariance matrix. Okay. And if you compare the W and the V, okay, you compare the W and the V here, basically you compare this expected value of W and V, it's going to be 0 because they are white noise, so all the random variables are going to be independent. Okay, so it's going to be 0 here. As a matter of fact, if you are looking at this, if you're looking at so G is not the same as K. Okay, so you're comparing the same white vector, but at a different value, G and K, so it's also going to be 0. So this is basically the independence. Okay. So overall, what we can write is, so W of K. So generally, you write it's a white noise with 0 mean and with a covariance matrix at here. And the V, it's basically it's a 0 mean too, and RV over here. Okay. All right. So if a scalar value, then this is basically just a single quantity scalar here. That basically is a variance, and a vector, and this is going to be a matrix at here. Okay. Yeah. So what do we want to do then, right? We want to basically, we wanted to, objective is do this. So here's your system, and input and output. Okay, and the system is noisy, right? There are different kind of noise in it. So then we wanted to design an observer. Okay. The same kind of an idea as before. So taking the previous input and output value, design an observer, and produce x hat of k. Okay, x hat of k. Okay, yeah, and that's basically observer here. So design an x hat of k, and what we want is, we want x hat of k to approach x of k, right? That's the ideal observer here. Okay, but however, right now the situation is you have a noise in it, so it's not a clean system. So x hat of k really doesn't matter how well you design it. X hat of k will not be exactly as x of k because of noise, right? So there will be some variations. Let's say x of k, maybe it's a 3. So the x hat of k, because of noise, is going to be a value around the 3, right? Yeah. And there's a variance in that. So basically, if you want x hat of k to be close to x of k, then what do we need? We need to reduce the what? The variance, right? If we can reduce the variance, then that's another. That's basically close to x of k here, right? So then if we define ourselves in an error, so that'll be basically x of k minus x hat of k. Okay, yeah, x hat of k. Then, due to noise. So what we want is, we want the expected value, E. We want the expected value of this guy, and which is, of course, according to our definition, which is this. Okay. We want this expected value to be 0. Okay. If it expected value to be 0, so that basically means this x hat, this x hat is going to be a good estimator of this x. Okay, that makes sense? Yeah. So In other words, the expected value of x hat of k from here will be the same as expected value of this, because that's a determinant, so it will be the same as this one here. Okay, it will be the same as this. Okay. And this is what we call a unbiased estimate. Okay, unbiased estimate. So why is it unbiased? Because the mean value, right, reflects the actual value there. Okay, that's unbiased. Okay. Now before we move on here, okay, when we're looking at this quantity here, the x hat of k. So if we set the k equal to 0, basically we're looking at is the initial condition there, right? Initial condition. So for k equal to 0, okay, so that e, okay, so if let's say we're looking for is what's the error covariance, right? Let's look at this for k equal to 0. So what is the covariance? So what is the covariance matrix, okay, for this error k? Okay, for this error k here. And that's actually one of the initial condition you will need to, okay, apply it here. So how do we define the error then, right? The error is basically it's E of 0 and the E of transpose 0, like this. Okay. Yeah. And in other words, so the E, okay, is x, okay, of 0, x hat of 0, then x of 0, x hat of 0 transpose like this. Okay, so we'll call that a p naught. Okay, p naught here. So that's going to be the error covariance for the E there. Okay, for the E. Okay. Now, if I write a general one there, okay, this is your basically initial condition. The initial condition basically means you're going to come up with a p naught, okay, before you started the process or simulation. So, in general, right, we define this. We define p of k plus 1. So let's look at the not the p of k. Let's look at this one here. So E expected value of k plus 1, expected value transpose k plus 1. Okay, so in general, let's look at the covariance matrix, okay, at the instant k plus 1. Okay, k plus 1 here. Alright, so which means basically you can replace x of k plus 1 at here minus x hat k plus 1 and x of k plus 1 minus x hat k plus 1 transpose like this. Alright, in general, this is the covariance matrix for the error E. Okay, for the error E. And error E represents the estimation error. Okay, estimation error. So remember what we said. We cannot have x of k to be the same as of x. We cannot have x hat of k to be the same as x of k. But what we can do is we can minimize the variance. Okay, the variance of this error, estimation error here. So you're not just minimizing the variance of one x1 or x2 of k, right? You're minimizing this variance for all of them. Basically, you're going to minimize the variance for this whole chunk at here, which means you're going to minimize this covariance matrix at here. Okay, so what we want to do now is basically we want to minimize, okay, this p of k plus 1. Okay. So this guy here is going to be basically a diagonal supposed to be a diagonal matrix at here, right? Yeah. Diagonal elements are the variance of the estimation errors. Okay. Yeah. So technically speaking, maybe let's say this is the error for one of the states x1 of k, and what you want is you want to minimize that. Okay. So when you have this kind of case set here, okay, this should be up here because the area underneath the distribution should be 1. So this is basically going to be better than this one that here, right? Going to be this one here. Okay. Yeah. Okay. So now let's look at how do we do this minimization problem here, right? Yeah. So minimizing this p of k plus 1, okay, let's look at, so this is our starting point and here, okay, this is our starting point. Okay, so now we're going to try to find basically different things now. We're going to have to define ourselves the observer we're using, okay, we're using here. So what observer we're going to use? This is very much similar to the observer design, okay, in the previous lecture. Now let's define our observer now. Okay. X hat of k. Okay. So what's the observer? Observer is this, equal to g x hat of k plus h u of k. Okay. Here's observer. Now yet and just like the observer design, so what do? We multiply, we use a so-called observer gain at here, but this time this is actually going to be called common filter gain at here. Okay, so then you have this is going to be y of k at here, subtract c x hat of k. Okay, like this. So this k of k here is the common filter gain. Okay. And this y of k, that's the output of the system here, right? Output of the system. What's the output of the system? Which is this quantity here, right? This quantity. Okay. So you can replace this guy here with that the expression. Okay. So this is a cx of k plus v of k. Okay. Plus v of k. So that's from our original system. Was that good? Yeah. Okay, so x hat of k is this. And what is x of k? X of k is the system, which is, so this is supposed to be what it is, right? But we are not too sure, basically. Actually, we need to figure out. Yeah. This is x of k plus 1. Okay, so what do? We're looking for minimizing this covariance matrix, basically where we have this error at here. We have this x minus x hat at here, right? X minus x hat. So use this equation, right? Let's see, this is number 2 and this is number 1. So use number 2 minus number 1 to obtain the error E. Okay, to obtain the error E k plus 1. Okay, to obtain this. Okay, so what do we get? If I use this, subtract this. So apparently this h here and this guy here, they will cancel each other, right? They will cancel each other. So this one, subtract that, plus this one, subtract that. Okay. Yeah. So we get g x of k minus, okay, here it's minus gx hat of k and minus the k common filter gain cx of k plus v of k minus c x hat of k. Okay, like this. That's the error, the estimation error. Apparently, it's a noise, right? It's a noisy signal because the W and because the V at here. So do a little cleaning in here. So gx of k, and then there is a gx head of k. So together, what do I get? We get this, right? Okay, we get this. At the same time, okay, if you look at this one here, you have the W at here. You have what's going on here? Oh yeah. Just a second here. Alright, so at the same time you have this is a k multiplied by c x of k. This is k multiplied by c x head of k here, right? So together you have this minus kc x of k minus x head of k. Okay, right? You have this term here, and the rest of them, there's a w of k, this guy over here. And there's another one, minus k, small k, just to differentiate this one. This one times what? Times the v at here, right? Times the v. Okay, yeah, so that's after cleaning would look like this. So these two terms here, this gx, this kc of this, and that can be written as what? That can be written as g minus kc. Okay, g minus kc. And x of k minus x head of k, according to our definition, is e of k. Right, so this is e of k here. Okay, it's e of k. And the rest of the term at here, okay, they're basically noise. So w at here, v at here, and then there's the u k at here. So let's define this one as stands temporarily as a variable here. Let's define it as n k at here. Okay, that's nk. Okay, so this is nk for this term at here. Okay, so now we obtain the expression for e of k. Okay, for e of k, the error. So what do? We plug this one back to where? Back to our covariance matrix at here. Right, this covariance. Okay, plug it here, here. Okay, right here, here. So which means basically our p of k plus 1, okay, our p of k plus 1, okay, is going to be expected value. Okay, there's a bracket here, there's another bracket here, okay, and finish the bracket. So the first bracket is basically move this over here, right? And then here, move here, there's transpose. Okay, so that's your p of k plus 1. Okay. So next step is, okay, so you have this guy times the transpose of itself. And what you can do is a linear algebra now. So this one times the transpose of this. So basically do the transpose first, right? So what's the transpose of this term here? So maybe I'll just write it. Transpose of this is the transpose of this plus transpose of this. Okay? And transpose of this is AB transpose, which will equal to what? B transpose times A transpose, right? Yeah. So that basically gives us this E transpose times the transpose of this, right? Transpose this, okay? And then plus N transpose. Okay, so no change for this one, and come back here, right? Yeah. And now you expand the brackets here, expand the factor, right? Multiply them out, okay? Multiply them out. So multiplying them out, and that requires a little bit carefulness at here. So once you expand them out, you will see that what happens is you're gonna get this. You're gonna get the G minus KC, right? Just kind of imagine this, right? This is G minus KC E plus NK here. Maybe I'll write it here, just for the ease of looking at it here. Okay, so multiplication. So what are we multiplying? We're multiplying this term with this term here, right? This term. So what do we get? This term out of that term, that get EK and E transpose of K here, right? E transpose of K. And the expected value of that whole chunk, you know, basically you can take all the constant out of the bracket, and that's basically E expected of K, E transpose like this, okay? And then G minus KC transpose. Make sense, right? That's the expected value of multiplication of this term with the multiplication of this term at here. Okay? Yeah. So same thing, right? You do the same thing. Basically, multiply this with that, then it'll be expected of the value of this multiplied by that. And then this term multiplied by this, expected value of this multiplied by that, right? Yeah. So you have a couple of more terms in here. So G minus KC, expected value of E times N transpose. Okay. And there's one more here, plus E expected value of N times E transpose times G minus KC transpose. Then there's another one, expected value of N times NT. Okay, like this, right? Yeah, that's what happens if you expand everything out. Okay. So now watch carefully. Expected value of the error E and N here. So what's E? E is a noise, and N is also noise associated with the W and the V at here. So you can prove that this term is actually going to be 0. Okay, so they are independent, and this term is going to be 0 too. Okay. So what you're left with is this guy and this guy at here. Okay. Is that good? So this is a P of K plus 1 equal to this by this by this, and then plus this. And what's E of this guy here? What is this term here? Here's a clock in the morning. P of K, what's the P of K here? P of K is the covariance of this, right? So then, how about this guy here? So what should we call this? This is P of K, right? It's P of K here. So now you got yourself basically sort of a recursive discrete difference equation now, right? Very close now. So the last term here, basically, what will be this guy here? And what we define here is W minus KV at here. So you basically, what you're going to do is you're going to put this over here, put that the transpose here, and do another multiplications out. Okay, do another one there. Okay, so what you're going to have is we can prove that this E NK N transpose K. Okay, if you plug everything into it, okay, you can see you can get this is RW plus KK and RV and KK transpose. Okay, you can get this guy here. Okay, and by the way, what will be the size of the gain matrix K? Kalman filter gain matrix K here. Okay, I noticed that when some people ask me the question, I mean, sometimes they got trouble with this proper size here. So what would be a proper size of a K based on this observer right here? So let's say suppose you have a single input, maybe single just for simplicity. If a single input, single output, what will be the size of K? Yes. Okay, it's n by 1, right? Yeah. If there's multiple outputs and there are m number of outputs, n by m, right? Yeah. Okay. Okay, so now let's sort this thing out. Now what do we get for this p of k plus 1 here? So this p of k plus 1 will equal to what? G minus kc p of k, then G minus kc transpose. Okay, so k, this k is this k here, so I just kind of neglected that bracket k in it, right? Okay, yeah. Then plus this term, so Rw k Rv and k at here. Okay, there we go. Okay, so this is the covariance matrix, and that's the P, and that's the relationship between your P and common filter gain K. Remember the objective. What's the objective? Objective is to minimize what? Minimize this guy here, right? So when you talk about minimize, you gotta say, you minimize with manipulating something here, right? So if you look at this equation here, the only one you can manipulate is which one? Is a K. So then the question here is, how do we obtain the optimal K such that this capital P is minimized? Okay, so basically minimize P, okay, with optimal K here. Here is optimal K. Okay. So now the question comes to this regular optimization problem. So what do? We do what? Partial derivative of this guy. We do first derivative test. First derivative test means partial derivative of this guy with respect to which one? With respect to the variable, right? You're manipulating. And then you do what? Set equal to 0, right? Set equal to 0. Then solve for the optimal value K. Okay? Then you get your critical point, basically. Okay. So here comes this. Okay, looking at this expression here, what would be the partial derivative of P with respect to K at here? Yeah. So now there is this and this and this at here. So there is a little trick at here, though, huh? You need a little matrix calculus. But let's see, if I consider this is a capital D at here, this is capital D at here. Okay, capital D and D. So then partial D, so for that particular one, for this term here, okay, for this term, it will be partial of this over K here, right? Over K here. Okay. So how do I calculate this partial derivative? So what you need to do is you need to use a chain rule at here first. So partial derivative of this with respect to D first, then partial D over partial K next. Okay, a chain rule. Okay, a chain rule. So in the previous lecture, when we learned optimal control, right? We actually derived. I showed you something already, right? So basically, you have X transpose. You have X A x transpose, what's the partial derivative of that respect to x? Right? Yeah, remember, but it's similar, right? This is basically like the 1/2 mx squared, that kind of structure here. Okay, but you can see that the first one here give you 2d p of k. Okay, give you 2d p of k. Then partial d over partial k. So partial d, this is a d at here. So partial d over partial k, that's a constant, gone. C is a constant, so you're supposed to get what? A minus c, right? But however, this is a matrix calculus, so you're actually gonna get negative c transpose. Okay? Yeah. You get a negative c transpose. That's essentially to keep the dimension here. We're talking about column vectors, right? Yeah. So that's the partial derivative of the first term here with respect to k. Partial derivative of the k second term, 0. And here is partial derivative of the k. And that's actually the same format as what? As I was thinking this one here, right? Let's think this one. So partial derivative of the other term, partial k rvk over this k, okay, that equal to 2. 2 what? 2k, yeah, 2kk and rv transpose. RV, not transpose, RV just, yeah. Right? Yeah. So, put them together. So, partial p of k plus 1 over partial k give us, what do it give us? It give us this guy plus this guy. And d, right, the d back is g minus kc. And then p of k. Yeah, that's right. And then there's a negative here, c transpose, okay, like this. And plus 2 capital K, small k, and RV. Okay, RV is the covariance matrix for the sensor noise, or the output, right? Yeah. So set it equal to 0. Solve for what? Solve for k, right? Solve for k. So now I got the kk equal to, so the 2 will be gone. So that's gonna be, what's that gonna be? Yeah, you're gonna have to multiply this out, right? So g multiply p c transpose, k c p c transpose, 2 then k rv. So combine the two things together, right? So move everything. So you will get this. Okay, you'll get this capital K equal to this. Now this is basically the capital KK is the common filter gain here, right? It's the common filter gain. Okay, yeah. So what do? We basically we go back. If I go back to observer, right? If we go back to the observer, that's where you use this guy here. Remember, when you design observer, that's not a key what we call it. So what we use L there, right? It's observer gain L. How did you get observer gain L again? You use actually pole placement, right? To basically use Ackermann formula. You designate desired pole's location. You can use Ackermann formula to obtain the observer gain L. Now this time is a slightly different approach. That K is obtained through this, okay, through this one here. The only trick now is we don't know what the P of K yet, right? We have to have the P of K in order to be able to calculate this K here. Okay, yeah. Is that good? So now combine this guy with your original, this one here. Okay, with your original this, and the original one is this guy here. P of K plus 1, where's that original one there? a mistake here. Okay. So 1 second. Yeah. So combine this with the original one there. G. So let me just rewrite this guy here. This term, right? This term. G minus case A. G minus case C. What is it? P of K. Transpose plus. Oh, it's a plus. Plus K RVK. Okay, no, plus this. So, and this one here, okay, and this one here you can actually simplify it a little bit. Okay, so basically you can, if you substitute, okay, because we obtained our optimal gain K. If we substitute this one into here, here, and here, and here. Okay, we substitute this one here, 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 and we can do a little simplification. Again, it's algebra here, so that P of K plus 1 can be simplified as this: RW plus G minus K, K, and C by P of K and G transpose. Okay, we can that can be simplified as this one here. Okay, so essentially now we have two equations. One equation is this 3 and 4. Okay, so two equations. So these two equations, okay, form ourselves, okay, a so-called the first kind of a common filter. We call that prediction type of a common filter. Okay, so equations 3 and 4. Okay. So equations 3 and 4 is called predictive type of common filter. Okay, predictive type common filter. So what does a predictive type of common filter means? As a matter of fact, that's exactly the same kind of format as the full order observer, the type of full order. Remember when we designed observer, we had a two type of observer, right? We call it observer, and then the second type is called current type of observer. Okay, so this is basically the same idea there. So predictive type of observer, the writing as this one here. This is K plus 1. Often in time, some textbook or reference they write it like this. So P of K plus 1 and the K. So it's the prediction of this K plus 1 instant based on the previous K informations. Okay, that's predictive type of observer here, right? Yeah. Now, but predictive type of observer is not what we often use at here. Okay. Predictive type often, what we use often is the next one, which is a handout that I gave you. It's the current type of common filter. Okay, so let me just tell you what the current type of common filter is. Okay. Current type of common filter. Okay, so current type of common filter, and I'll just put down the formulation now, but without doing this all the partial derivatives anymore. Okay, same system, right? And same objective. You want to minimize the covariance matrix. Now the observer you designed is basically now is in this format. okay, is this x hat k plus 1, okay, vertical bar k equal, okay, g x hat k plus h u of k. Okay. So this is called this is a predictive estimate. So this is k plus 1 k. This is predictive estimate here. All right. So if you remember, actually, where did you see this notation here? Something slash something slash and then something in here. Conditional probability, right? Yes. Okay. So basically, you have this. If you have this previous information, then what will be the probability of this k plus 1, right? Yeah. And the next, this is a predictive part, and the next one here is a filter, also called basically based on the current information here. So next one is, okay, x of k plus 1 k plus 1, and that equal to x hat k plus 1 k, okay, plus the common filter gain k plus 1. Okay, so don't mix up the k here. This k is common filter capital K. This is small k here, right? Bracket y of k plus 1 subtract c x hat k plus 1 vertical bar k. Okay, yeah. So the current type, okay, observer. This is basically current type observer. If you remember, if I open up the observer design, if I open up observer design, if you look at the observer design portion, right, same idea. Look at this guy here. This is the, when we design for observer, this is what we call the predictive, we call the Leuenberger observer, right? So look at this one here. This is not the same format, right, as when we design the predictive type of common filter, right? If I look at this current type there. Where's my current type? The current type. This is not the current type. Yeah, the current type I said is optional for undergrads, but for, you see this right here, this is the current type observer here. Okay, you see the similarities here, right? See the similarity? Yeah, it's the same structure basically, right? Same structure. Okay, so now the question here is, okay, same thing. The objective. What's the objective? The objective is to, okay, to find this to find this common filter gain, okay, to find this guy such that this p of k plus 1 k plus 1, okay, is going to be minimized. Okay. So what's p of k plus 1 and k plus 1? And that's the error covariance. Okay, this is the error covariance. Okay, this is the error covariance here. And E equal to this, okay, equal to x of k plus 1 minus x hat k plus 1 k plus 1. Okay, yeah. So here's the observer, here's the objective, to find this optimal gain such that error covariance is minimized, and the error is defined between the actual value minus the estimation, right? This is the current estimation, right? This is basically the x of k plus 1 k plus 1. Why is it current? Because you're taking the current output information into this equation at here, right? Okay, yeah. So basically same process now. So what do we do next? Next is you need to find the expression for e of k plus 1, just like what we did in the previous step, right? And then plug it here, expand everything, right? And then take a partial derivative, to find optimal gain k. Okay, same idea, yeah.
What's the definition of, for example, x k plus 1 k plus 1 or p k plus 1 k plus 1?
So those are basically estimated here, right? The difference, as I said, k plus 1 slash k plus 1 or k plus 1 slash k, it's basically it's a matter of what the information you're using here. So for example, when you see this k plus 1k, so what we're saying is this is a prediction. This is the prediction of this x of k plus 1 based on what? Based on previous values. You know what I'm saying? Previous ones. Okay? Yeah. So basically, if you write x hat k plus 1 of k, so this is basically the estimate based on k minus 1, and 0, all the previous information is there. Okay? And when you have this k plus 1 here, you included the current output information, right? Because k plus 1 is what we call, it's becoming the current estimate now. Okay, yeah. And same thing for this p here. If this is a p of k plus, the definition of this one here, that's the error covariance, because you're looking at is the difference between x of k plus 1 and x of hat k plus 1 k plus 1. Okay. So as a matter of fact, there is a p of k plus 1 of k. Okay, there is a p of k plus 1 of k, and that one is defined as this. So that one is defined as x k plus 1 minus x hat k plus 1, and then what? K. Okay, that's defined as this one here. Okay, so actually we will be able to get a discrete Riccati equation for this one here. So this one here, this is not the first of all, this is another error covariance here. Okay, another error covariance, but this is not error covariance you're minimizing. The error covariance you're minimizing is this one here. Okay, it's this one. But from the handouts that I gave it to you guys, I'll be able to write down another one here. I'll show you, which basically is a Riccati equation. Okay, for this term at here. Okay, for this term. Okay, but just hold on a second here. Okay, it's time to connect all the dots though. Okay, connect all the dots. Yeah. Was that good? But to save me some steps of this, and also to save your boredness here, so we're not gonna calculate this and subtract to the partial derivative. But then what you do next basically is the handout. What happens there? Okay, you basically will end up with your this table here. Okay, basically you end up with this table. Okay. The common filter gain is going to be equal to this one. Okay, going to be equal to this one. And the error covariance, capital P, is going to be this guy here. Okay, it's going to be this guy. Okay. Yeah. Was that okay? So even the mathematics behind the theory here is, it's been probably spent a couple of pages to derive everything. But actually, when it comes to implementation, all you're dealing with are the equations here. So what do we have? First, this portion, that's a system model, right? A system model. And then you have initial condition. You have common filter gain k here. So That's just one line of code, right? That's one line of code. You're going to do the calculation. This is another line of code, another line of code, another one. So how many lines? 1, 2, 3, 4, 5. Basically 5 lines of code. That's going to give you the common filter here. Okay, it's going to be in a loop, of course. You're going to do a loop, recursive things here. But in terms of implementation, that's all you need at here. That's all you need. How do you do the implementation? The first page of the handout I'll give you this illustration of how to do the implementation at here, right? Yeah. So first come up with the initial condition, initial estimation, and the initial covariance matrix P naught. So that can be anything you want, okay? The initial estimation doesn't have to be necessary to be the same as the actual initial condition. Okay? It doesn't have to be. Okay? And this matrix here, in general, this matrix, the higher value of this matrix, initial value of this matrix, indicates less confidence that you have regarding the initial errors, basically. Okay, yeah. So then you implement this and that. Yeah, there's some names to call it. You can. This is what we call this step called time update, or prediction. And then this part is a measurement, or we call the filtering. Okay, yeah. And the last state is increase that, and then you go back and then do again. Okay, yeah. Was that okay? So okay, now which is not in the handout, I want you to look at your handout here. Okay, look at this equation here. Okay, so I copied it here. And this equation and one more equation and this equation. Okay, so let's manipulate, okay, based on the 3 equations at here, right? Manipulate it a little bit. So how do I manipulate? I'll start it from here, okay? Starting from here. So P of k plus 1k equal to this plus RW, right? And what is the P of kk? That's gonna come from here, okay? Coming from here. This is a P of k plus 1, k plus 1. So if I'm looking for P of kk, so what's it going to be? This is a P kk. This is going to be what? K minus 1 here, right? And this is going to be k, and k minus 1 there, right? So this is going to be G P of k minus 1 minus capital K, small k, say capital P k minus 1 plus RW. Okay, plus RW. Is that good? Yeah. So substitute k of k. So what's k of k? Basically replace this k plus 1 with k. So that's P of k minus 1, P of k based on k minus 1, C transpose RV, C, P of k minus 1, C transpose inverse, right? Inverse. So substitute this one into here, okay? Substitute this into here. Expand everything. Okay, expand. Oh, I missed the G of transpose here, right? There's a G transpose here. Okay, expand everything. So after expansion, what do we get? We get this P of k plus 1k. Okay, so P of k plus 1k equal G P of k minus 1 G transpose plus RW minus G transpose. You know, maybe I'll write RW later, just at the end. Let's write this term first. Minus G transpose. Sorry, not G. G. P. K. K minus 1. C transpose. RV. C. P. K. K minus 1. C transpose. Inverse. C. P, K, K minus 1, and G transpose, oops, and then G transpose, plus the last term, RW. Okay, so now we get this equation here, okay, this equation. Okay, so now before you move on here, so let me bring another one here. So when you look at this one here, now, if anybody have studied, what does that look like actually? In the optimal control lecture, where's optimal control here? In optimal control, what was the this thing looks yeah, well, maybe look at this one here. So what do we call this? Is a P of K, right? It's P of K here. This is the equation we obtained from the derivation of optimal control. Remember, what do we call this equation? What do we call this equation? That's what? That's the Riccati equation, right? That's the Riccati equation. So you look at this Riccati equation here. If compared to this one, there's a slight difference, but actually if I expand the second term, expand the second term, so G transpose P, move the G here, right? G transpose P times everything, then the G here. Compared to this, so this Q is that what? This RW here. This GP GT, that's the G transpose PG of this term here. And the next one is minus G, P, K, this whole chunk. So the C at here is actually which one? It's this H at here. You see the similarity here, right? So basically, this guy here, that's the Riccati equation. That's the Riccati equation in the common filter at here. Okay, that's the Riccati equation. But there's a fundamental difference between these two Riccati equations though. What's the difference? This one is, remember what we call this? This is K here, but this is what? This is K plus 1. So that's a backward Riccati equation here, right? But this one, look at that. That's what? K plus 1, K, 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 K. This is the forward one. Okay? This is the forward. Okay? As a matter of fact, this one, if you look at this equation here, okay, if you look at this one here, if I wanted to solve for P of K plus 1K, right? If I wanted to solve this one, actually, I don't need to know any evolution of the system state. I can offline calculate all of this one here, basically, before you obtain any observations. Can you see that? See, G is known, RV/RW is known, and all you need to do is just plug in an initial condition. Let's say initial condition is 0, -1, or you call it P1, 0, right? Initial condition. In IC here. Let's say you plug initial condition of this. Okay, then recursively you will be able to get all the rest of the P of K plus 1K here, right? Yeah. So that's basically this way. In MATLAB, okay, there's a command called DLQE. Okay, so when you apply the MATLAB command, what you're gonna get is, okay, DLQE to just see. So what you're gonna use this is this way here. So it's K P Z E equal to DLQE. Okay, DLQE. So what do we plug in here? We plug in G matrix. G matrix is a system matrix. Okay, it's a G matrix system matrix. So let me go back to my noisy system there. Where is it? Right at the beginning. So G is here. Okay, G is here. Now to use that command here, you have to be careful here. For the W, I have a column vector here. Okay, I have a column vector. So basically, what you have here, okay, it's an equivalent. You have an identity matrix, right? Identity matrix times this one here, right? Yeah. So there's an identity matrix I. Okay, identity matrix I. Okay. So you need to plug in the I at here. Okay, plug in the I over there. Okay, then C matrix, RW, and RV at here. Okay, so what this function will spit out is the common filter gain. So this is a common filter gain. Okay, this is common gain. And the Z is the error covariance. Okay, it's the error covariance. The P here is a solution of this Riccati equation here. Okay, that's a solution of this Riccati equation. And E is the closed loop, basically the closed loop based on estimator, the closed loop pose. Okay, closed loop pose here, right? So that's how you use this MATLAB command DLQE, right? However, you don't really need to always use the DLQE to calculate the common filter gain, and as in my lecture you will see that you can simply implement, okay, you can simply implement the formulas over here, or equivalently the one down the table here, to obtain recursively to obtain the gain of K. So let me show you an example here. Okay, here's the double integrator. After discretization, this is your discrete model. Okay, so now let's suppose we have a certain kind of a noise at here. Okay, and we're going to design a common filter at here, right? Yeah. So in this case, I'm assuming that I only have one noise, okay, basically on the second states, okay, which is the velocity there, okay. Yeah. So define RW, RV, okay. How do we calculate common filter gain? You see this while loop right here. That's basically implementation of this table here. This one. So I implement this one here. Okay. 3 line of code. Okay, 3 line of code, and we can get, okay, the common filter gains at here. Is that okay? Yeah. So study this, and how would you implement this, okay, recursively? If you want to use a MATLAB command, the other example here, use MATLAB command here. So W at here, okay, all the covariance for the noise. Just use DLQE and then K like this, right? So what's returned here? The K will be the common filter gain. Okay, yeah. Was that good? Yeah. So there's a slight little bit of time here. Next lecture, please bring your computer. So we're going to build a common filter all together, right? So this is basically the bigger picture is this. when you double click on this random process, and that's going to be this one here, okay? And when you double click on this common filter, okay, it's going to be this one here, okay? Only this in your handles. So if you can run a simulation successfully like this, then this model here, you can replace that model with the model, experimental model in the template, right? And you don't have to do anything in here, okay? And you will have your desired common filter response at here, right? And in the last lecture, I showed you very simple. Common filter plus the optimal control LQR is going to be the LQG, linear quadratic Gaussian control. Okay, yeah. So bring your computer and let's program that you can learn a little Simulink at the same time. Any questions?
When is the
Yeah, the project is supposed to do April 7th, right? But I can be a little flexible if everything is busy. So you can give me our final exam is on April 14th. Okay, so you can give me, let me see. How about Friday, April 11th? I'll send an email. April 11th is the deadline here.